Here you see a MATLAB live script, and I want to show you a few basic things in MATLAB. First, we define a vector in different ways. So an arithmetic progression 1 double column 7 gives you a row vector which has the entries 1 to 7. You can also do the same with a linear arithmetic progression with non-integer step width. Then you're going from 1 to 2 in steps of 0.3. Of course, you're only taking those values which are up to 2, including 2. So in this case, 1.9 is the last one. You could also say, I want to have arithmetic 3 is a linear spacing from 1 to 2 with 4 entries, or let's say 5 entries. Then you would get, and around this, an arithmetic progression where you have 5 entries, including the boundary values from 1 to the end, which is 5, a part which is 2, and which has altogether a vector of length 5. Now, for matrices, you have here one matrices, so it's the ones of dimension 3. If you are saying 3, 4, you get the rectangular matrix with all ones. The identity operator is, of course, given by the unit matrix. And test matrix can be created in the following way. You take zeros, so a zero matrix first, and then you insert, this is a command filling in the content of a matrix into a scheme. So you have 9 entries in a 3 by 3 matrix, and you fill in the values 1 to 9. So in this case, it means that that was a mistake. T3 should be, of course, filled in, and that should give you a matrix with the values 1 to 9 as in the columns of the matrix. So you have 3 columns, and the first one is going to contain the first 3 vectors, then the second column, and then the third column is filled in. Of course, you can create random matrices here of size 3 by 4, or complex matrices or complex vectors. So here you have a vector of length 4 created as a column vector with random values. Now, the X Hermitian or X prime is the conjugate and turning a column vector into a row vector, and the row vector into column vector. Now, each complex valued or real valued vector has a length, which is computed here in this way. And as we know, it's the square root of the scalar product. How do you get the scalar product of such a vector, of a column vector? You're taking the inner product, and this is done by turning X into a row vector by conjugation. So this is, so to say, the second argument of the scalar product, and you take this. So please take a look at this. It's not so obvious, but it's quite useful. Now, the next step is to show you what the Gauss elimination is doing. So Gauss elimination is bringing a matrix into row reduced echelon form. Therefore, the command is called RREF, reref. So we start with the random matrix of size 4 by 4, but we replace the third column. This is the symbol for the third column, but 2 times the first column minus 1 times the second column. And then we apply the row reduced echelon form. And what you can see here is obviously the fact that you have pivot elements in column number 1, 2, and 4, whereas the column number 3 does not contain a pivot element, but, and that's something quite underrepresented in standard textbooks on linear algebra, you find here the coefficients. So the linear relationship between the columns of the first original matrix and of this matrix are the same. So saying that you have the entries 2 and -1 in this column after doing this Gauss elimination means you're having 2 times what is you find in the first column -1 times what you have here. So this is exactly the same linear relationship. So recall that the Gauss elimination is represented by multiplication with elementary matrices from the left, and these leave the row space invariant, but also leaves the linear relationships between the columns of the original matrix and the new matrix intact. So here you have the same relationship between the columns. That's why you can read of this. Now, such a matrix apparently has rank 3 with 3 individual vectors. So the row-reduced echelon form has a basis with 3 elements, the 3 rows that you have here, or you're going back to the original matrix and you find out the columns number 1 to 2 and 4 form a basis for the column space. So to reduce the matrix, throw away the third column is to take from the matrix all the entries in the sense of all the row numbers, but column numbers only with labels 1, 2, and 4. And then I'm applying the Gram-Schmidt process, and I have a special routine that I call Gram-Schmidt-Feichtinger. And so you see I can do this. And then I can say, well, if you're giving me an orthonormal basis now for the column space, I can define the projection or compute the projection operator to a vector by first applying this coefficient mapping and then applying the synthesis mapping. Or you can do it by the combination of B with the pseudo-inverse. So this compare normed version is just telling you that you're having with the same size 2 matrices which are equal. You could also take the orthonormalization command. So this is a command creating an orthonormal basis directly from the matrix. And then you use it in order to do the projection operator, and that gives you the same thing. So for now, I'm stopping my recording.